Okay, so let's do a little example here involving a non-ideal Brayton cycle. So remember, the Brayton cycle utilizes a compressor which compresses the air, a combustor where the heat addition occurs, perhaps isobarically, perhaps not, and then work is extracted by the turbine, and some of that work or power is used to drive the compressor, and the remaining, or what is left over, if we subtract the compressor power or specific work, is the net work produced or net power produced by the gas turbine. This whole thing is the gas turbine. So let me put up the TS diagram here. Well, let's go over the givens first. So we have an inlet temperature into the compressor, T1. We have a pressure ratio, a compressor pressure ratio, the ratio of P max over P min, or if you like, P2 over P1, that's the pressure ratio, and is 8. So the compressor pressurizes the air by a factor of 8 in terms of the ratio of inlet to outlet pressure. The maximum temperature, presumably that occurs after the combustor, so that's T3. The maximum temperature is 900 degrees Kelvin. So we heat up the air by up to 900 degrees Kelvin. The net power produced by the gas turbine, the total power produced by the gas turbine is 15 megawatts. And the isentropic efficiencies for the compressor and the turbine are 80 and 86% respectively. These are not isentropic turbines and compressors. Okay? Now let's make a few assumptions here. I don't see any actual explicit statement, but let's assume that there's no pressure drop across the combustor. I don't see that there's a delta P across the combustor in the given. So I'm going to write here, I'm going to assume isobaric combustor. Isobaric combustor. I also don't see it, but I'm going to assume it. I'm going to assume adiabatic compressors and turbine. I don't see anything here, but there's really no way to calculate the heat rejection or addition in the turbines and compressors. I have no information, so I'm going to assume adiabatic compressor and turbine. Okay, adiabatic compressor and turbine. We'll move on from there as we need to. Let's draw the TS diagram, therefore, for this process, for this device. So we have a state 1 is the inlet. Let me put in my P min. Let me put in my P min and my P max isobar. That doesn't look good. So here's my P min, and here's my P max. P min and P max isobar. So we're compressing in the compressor, the air starting off at state 1. The isentropic process, if this were an isentropic compressor, this would be state 2 sub S. Sub S means constant entropy. But we have an isentropic efficiency less than 1. So we're going to have some irreversibility inside of the compressor, and therefore some entropy generation, and therefore a delta S within the compressor. So this is state 2, an increase in entropy from state 1 to state 2 because we have irreversibilities occurring inside the compressor. Then we have, apparently, isobaric heat addition in the combustor. So we have Q combustor, isobaric. We don't have a delta P across the combustor. Up to state 3, and actually we have temperature T3. That's our maximum temperature. So let me put up the initial and final and maximum temperature, the low, the minimum, and the maximum temperature here. So this is 310 degrees Kelvin. That's the minimum temperature, and the maximum temperature is 900 degrees Kelvin in the cycle, okay? Min and max temperature. And then we have expansion in the turbine. It's going to be irreversible, so there's going to be a delta S compared to the isentropic expansion process. So we expand from state 3 to state 4. There's a positive delta S because we have entropy generation, and therefore delta S is positive through the turbine. And then we have the heat rejection process going on in the environment, okay? All right, so let's get started here. Let's get started. Let's calculate the net power or net work. Looks like a lowercase w net, so I want specific net work, so analysis. I guess I want to erase this too. So this is a non-ideal Brayton cycle. No pressure drop across the combustor, so that simplifies things a little bit. So I want to find W net. Now, W net is the difference between the turbine and compressor power, or work per unit mass. So assuming the m dot is all the same throughout the cycle, assuming the m dot is all the same, then the difference between the compressor and turbine power is the net. Okay? So let me write here, W dot net is equal to W dot turbine minus W dot compressor. Now, if I divide everything by m dot for the air, and we assume m dot for the air is constant, m dot's constant throughout the cycle, then I get W net is equal to W of the turbine minus W of the compressor. So I need to find the compressor and turbine specific work, and then I'll have W net. Okay, well, let's find the compressor specific work first. So let's look at process 1 to 2. That's compression in the turbine and the compressor. Compression. That's the compression process in the compressor. So if I apply the energy balance, to my open flow compressor, it's adiabatic. Work is positive, compressor work is positive on the system, not by the system. And if I assume no changes in kinetic and potential energy, I got no information about kinetic and potential energy of any of the flows in this device. So I think I'm going to say delta KE equals delta PE 0 for every device. So I'm going to neglect kinetic and potential energy in the energy balance. If I do all that, I get a open system energy balance yielding W dot compressor is equal to m dot H2 minus H1. Now I can divide both sides by m dot, and I get specific compressor work is equal to H2 minus H1. Now I know H1, but I don't know H2. I need to know a temperature at state 2 or something. All I know is the pressure. I need a temperature to go to a table and extract out H2. So I don't know what this is. And frankly, there's no way to get it. Okay? So this is not going to help. Let's do the following instead. Instead of looking at process 1 to 2, let's look at process 1 to 2 sub S. Process 1 to 2 sub S. This is the isentropic compression process. Let's look at 1 to 2 sub S. Now, why would I be interested in looking at 1 to 2 sub S? In other words, the reversible compressor? Because this isn't going to help me, but this will. The definition of isentropic efficiency of a compressor is W dot of the isentropic compressor divided by W dot for the actual compressor. Of course, I can divide this by mass flow rate and I get W isen compressor divided by W compressor. And therefore, the real compressor work, W compressor, is equal to the isentropic compressor specific work divided by the isentropic efficiency. Now, I have the isentropic efficiency. I don't have the isentropic specific work for the isentropic compressor, but maybe I can get it. So let's look at process 1 to 2, which is a process for the isentropic compressor. If I apply the energy balance, I get W isen compressor is equal to H2 sub S minus H1. That's from the energy balance. No change in kinetic and potential energy, no heat transfer, steady state. It's all steady state. Okay, so I know H1. I don't know H2 sub S. So H2 sub S is equal to H2 is equal to H evaluated at a pressure P2 and S2 sub S equals S1. So it's an isentropic compression process where pressure is equal to P2. Well, if this is an isentropic compression process, then it means that PR2 sub S over P1, PR1 is equal to P2 over P1. If you want to be cranky here, I can do a P2 sub S, but P2 sub S is just the maximum pressure P2. So this is P2 over P1. Now, P2 over P1 is our pressure ratio. P2 over P1 is our pressure ratio. P2 over P1 is R sub P, or our pressure ratio across the compressor. So this is R sub P. Let me put up the TS diagram while we're doing this, just to make sure that we're all on the same board. So this is P1. This is P2. This is state 1. This is 2 sub S. And this is the actual compression process 1 to 2. Okay? So that's what's going on right here. So we're looking at 1 to 2 sub S. 1 to 2 sub S, which is isentropic. Okay? Okay, so this means that P R2 sub S is equal to PR1 times the pressure ratio. Let's see here, PR2 sub S, what is that? Not a lot of room here. I'll write it right over here. PR2 sub S is PR evaluated, PR1. PR1, let's find PR1. PR1 is PR evaluated at T1, which is 310 degrees Kelvin. 310 degrees Kelvin. T1 is 310 degrees Kelvin. Going to tables, PR1 is 1.55. 1.55. Maybe I can get a couple more decimal places there. And that's from IGB tables, 1.555. Okay, so 1.555, the pressure ratio is 8, and I get a PR2 sub S. PR2 sub S equal to 12.44. 12.44. 12.44. So PR2 sub, so H2 sub S, so this is H evaluated at PR2 sub S, which is 12.44. And I look up H at PR2 sub S of 12.44, and I get H2 sub S 562. 562 kilojoules per kilogram. Okay, so now I have H2 sub S. Let's see here. Oh, what's H1? I don't have an H1. Let's see here. Do it over here. H1 is H evaluated at T1, which is 310 degrees Kelvin. Should be about 310 kilojoules per kilogram. Let's see here, 310 kilojoules per kilogram. And that's from IGB tables. IGB tables. Okay, so W Ison compressor is 562 minus 310 kilojoules per kilogram. And I get an isentropic compressor work. Isentropic compressor work per unit mass of 562 minus 310, 222 kilojoules per kilogram. So that's the isentropic compressor work. Okay, so I now have the isentropic compressor work. Let's see here, 222 kilojoules per kilogram, and then I divide that by 0.8. The compressor isentropic efficiency is 80%, 80%, and I get a specific work for the compressor, whoops, divided by 0.8 of 277. Oh, running out of room. 277 kilojoules per kilogram. Kilojoules per kilogram. Notice that the isentropic compressor takes less power than the real compressor to pressurize the flow up by a factor of 8. Okay? So let me write this somewhere. So W compressor is 277 kilojoules per kilogram. All right? I'll write that somewhere. I need to write that somewhere. Okay. All right, so now we need to find W turbine. We need to find the turbine specific work. So let's look at process 3 to 4. Let's look at process 3 to 4. Process 3 to 4. This is expansion in the turbine. Again, if I write the energy balance, I'm going to get W turbine is equal to H3 minus H4. Assuming no heat transfer, steady state, steady flow, no changes in kinetic and potential energy. I know H3. How do I know H3? Because I have the temperature. I have the maximum temperature at state 3. Let's actually see if we can crank that out. So I know H3, T3, 900 degrees Kelvin is the maximum temperature in the cycle. So I can get H3. So I do know H3. I do know H3. let's see here, H3 equals H evaluated at T3, which is 900 degrees Kelvin. And I can crank that out pretty quick. From tables, let's see here, H3. It's in here somewhere. Yes, 932 kilojoules per kilogram. 932 kilojoules per kilogram. Okay, I get that from tables, no problem. So I know this. I don't know H4. I know the pressure, but it's an irreversible turbine, so it's not a constant entropy process. So this, I don't know H4. This doesn't get me anywhere. So I can't do this. Like with the compressor, I can't do this. But I can use the definition of isentropic efficiency. So efficiency for the turbine, isentropic efficiency, is defined as the actual work from the turbine divided by the isentropic work of the turbine. I'm running out of chalk here, okay? In other words, dividing by m dot, W turbine is equal to eta turbine times the isentropic turbine specific work. Now, I know the efficiency for the turbine, it's 86%. 86%. So now I need to evaluate the isentropic turbine work. So let me put up the TS diagram for the turbine. So here's S, here's T, here are my, it doesn't look good. Here are my P min and P max isobars. So here's state 3. The isentropic turbine goes down to 4 sub S. The real turbine, the actual turbine, increase in entropy goes to state 4, okay? So process 3 to 4 sub S, this is isentropic turbine work. So again, energy balance, I get W turb isen equals H3 minus H4 sub S. H3 I've got, 932. I need H4 sub S. How do I get H4 sub S? Well, PR4 sub S over PR3 is equal to the pressure ratio, P4 over P3. Or if you like, this is P4 is the minimum pressure, and P3 is the maximum pressure. So this is 1 over the pressure ratio. Okay? Isentropic process. So PR4 sub S is equal to PR3, 1 over the pressure ratio. So what's PR3? Let's see here. PR3 is PR evaluated at T3, which is 900 degrees Kelvin. Let's see here. What's PR3? I can get that from a table. PR3. 75.3. 75.3. And that's from a table. Okay. So I get 75.3 times 1 over 8. So let's divide that by 8. And I get PR4 is equal to 9.4. 9.4. So H4 sub S is H evaluated at P4R4 sub S, which is 9.4. So H4 sub S I can get out of a table, and I get 519.32. 519.32. kilojoules per kilogram. Okay, I have H3, I have H4. So I've got 932 minus, I'll just do 519. 519 kilojoules per kilogram. And I have the specific work for the isentropic turbine, the most efficient one. The most efficient one, I guess I better crank this out. 932 minus 519, or 413 kilojoules per kilogram. Okay? So the work for the turbine is the isentropic efficiency, and that is 86%. So 0.86 times the specific work for the isentropic turbine. So 86% of 413. I get 355. 355 kilojoules per kilogram. So the specific work for the turbine is 355 kilojoules per kilogram. Okay? 355 kilojoules per kilogram. Okay, now I know the net work. So 355 minus 277. The net work is only 78 kilojoules per kilogram of airflow through the compressor and turbine. Okay? 78. So the net specific work is 78 kilojoules per kilogram. That's it. The compressor power is 277. Compressor work, sorry. So W compressor is 277 kilojoules per kilogram. And of course, the turbine work is 277 plus 78, which was 355. Okay, so let's box this up somewhere. So W net is 78 kilojoules per kilogram. So let's box this up somewhere, okay? That's W net. Okay, let's calculate this thing called the backwork ratio. The backwork ratio gives you an idea of how much power is required to run the compressor compared to the power produced by the turbine. In fact, it's the ratio. It's W dot compressor over W dot turbine. Backwork ratio. W dot compressor over W dot turbine. Backwork ratio. Backwork ratio equals W dot of the compressor divided by W dot of the turbine. And we can divide top and bottom by M dot for the air. In fact, I had to write the assumption down here. We are assuming that the airflows are the same throughout the device. So I'm going to write here M dot equals M dot air for all devices. Why might that not be true? Why might the mass flow be different in the real world in these devices? The reason is because we are adding fuel and therefore heat. Q dot combustor. We're actually adding fuel into the combustor, not very much. By mass, maybe 1 or 2% of the airflow. We're adding a little bit of fuel and we're burning it. So the mass flow rate through the turbine is a little bit larger than the mass flow rate through the combustor, but we're not through the compressor, but we're not worried about that. We're not worried about that. We're going to assume the mass flow rates are constant. Okay? So I'm going to divide top and bottom by M dot air Okay, and I get W compressor over W turbine. Well, I've got W compressor, that is 277 kilojoules per kilogram. And I got W for the turbine, which was 355, as I recall. 355, yep, kilojoules per kilogram. These cancel out, and I get a backward ratio, 277 over 355. 277 over 355, I got it. Let me crank it out, my calculator. Probably about 80%. Almost 80%. 78%. Okay, 0.78, 78%. Three quarters of the power produced by the turbine gets used to drive the compressor, only leaving a quarter left over. Okay, so that's my back work ratio. Let's see, so let's put that in a box over here. Back work ratio. Clearly, the higher the back, you want a fairly low back work ratio. Back work ratio 0.78, or if you like, 78%. Clearly, you want a gas turbine with a fairly low back work ratio. And you do that by improving the efficiencies of the turbine and the compressor. Okay, what's next? We're supposed to calculate m dot for the air. How much air is flowing through the device? So I wanted to know what m dot air is. Okay. So I want to know what m dot of the air flowing through the gas turbine is. So I want to know what the m dot is flowing through here. Now, luckily, we know what the net turbine work is. It's 15 megawatts. So actually, W dot net is 15 megawatts. Okay? W dot net is 15 megawatts. So let's write W dot net, which is, by the way, equal to W net times m dot for the working fluid, which is air, is equal to 15 megawatts. Okay, so I've got this. I've got W dot net. Okay, so let's solve for m dot air. M dot air is equal to W dot net divided by the specific net work. Let's see here. So we have 15 megawatts. The net work was 75 kilojoules per kilogram. No, I'm sorry, 78 kilojoules per kilogram. I got to convert kilojoules into megajoules. Oh, let's see here. So there is, for 1 megajoule, I got 1,000 kilojoules. Okay, so we have some unit conversion there. The kilojoules cancel out, and I have a megawatt, a kilojoule, and a kilogram here. The kilograms go upstairs. A megawatt, by the way, is a megajoule per second. So I'll end up with kilograms per second, which is a unit of mass flow. Let's see here. What have I got? What do I do with my calculator? Where is my, here it is. So 15 times 1,000 divided by 78. And I get 192 kilograms per second. 192 kilograms per second. 192 kilograms per second of air. That's a lot of air. That is a lot of air. Okay? So m dot, 192 kilograms per second. 192. Let's see here. 192 kilograms per second. So m dot, 192 kilograms per second. 192 kilograms per second, okay? There we go. Okay, so let's move on here. Let's move on. Let's now calculate the heat addition. Let's calculate Qin. Let's calculate Qin. Qin, or Q in the combustor. If I apply an energy balance to the combustor, so I apply an energy balance to the combustor, no changes in kinetic and potential energy, no work interactions, I get H3 minus H2. I already have H3, I calculated that previously. I don't have H2. H2 is the compressor exit enthalpy, specific enthalpy. So let's look again at process 1 to 2. Process 1 to 2. So here's my TS diagram. TS. Here's my min and max isobars. Here's the isentropic process. Here's the real process in the compressor. Okay? And if I apply the energy balance, I get W compressor is equal to H2 minus H1. So W compressor is equal to H2 minus H1. H1 I have, the compressor work I have, so I get H2 is equal to work compressor plus H1. Let's see, the compressor work, specific work was 277. 277 kilojoules per kilogram, and then H1 was 310 kilojoules per kilogram, and so H2 is equal to 587 kilojoules per kilogram. So now I have H2. H3, what was H3? As I recall, that was H at temperature T3, which was 900 degrees. So I get 932 kilojoules per kilogram. 932 minus H2, which is 587 kilojoules per kilogram. And I get heat addition. Heat addition is 932 minus 587, or 345 kilojoules per kilogram of airflow. So let me write what my Q dot is in the combustor, or my Q in the combustor. So Q combustor is 345 kilojoules per kilogram. Okay, 345 kilojoules per kilogram. Okay, so let me write it here. Q combustor, 345 kilojoules per kilogram. I'm going to box that up too. A lot of stuff to calculate here. A lot of stuff to calculate. So that's the Q in is my Q combustor. Okay, let's calculate the efficiency. Well, this is easy to do. Efficiency is just W dot net over Q dot in. So the efficiency of this thing this Brayton cycle equals W dot net over Q dot in. So if I divide by the mass flow, I get W net, because the mass flow is the same everywhere, Q in, and my Q in is my Q combustor. So I get W net over Q combustor. Oh, what was my W net again? 78 kilojoules equals 78 kilojoules per kilogram. And then Q combustor was 345 kilojoules per kilogram. Let's calculate that. And I get 22%, or 22.6%. Okay? So the efficiency of this device, the thermal efficiency of my Brayton cycle here is about 22%. So eta 22.6%. Okay. 22% of the energy added to my system or taken in by the system, the device is converted into usable work. Only a quarter. Let's compare that to the Carnot cycle. Let's say instead of having this thing here, this Brayton cycle with all these irreversibilities going on, what if we had a Carnot cycle doing the same thing? What if we had a Carnot cycle doing the same thing? So we have a Carnot cycle operating between a maximum temperature in the cycle, Carnot heat engine, and this thing is running all the time, rejecting heat at the lowest temperature in the cycle. So T min, T max and T min. T max and T min. So it's producing W dot, taking in Q dot high, rejecting Q dot low. Let's figure out what these min and maximum temperatures are in the cycle. So we're going to put a Carnot cycle between these min and max temperatures. Well, the maximum temperature in the cycle is 900, so the heat has to be received at least at 900 degrees Kelvin, and the minimum temperature in the cycle is 310, so the heat has to be rejected at least at 310 degrees Kelvin. So the min and the max are 900 and 310. So the efficiency of the Carnot, or if you like, the maximum efficiency of any heat engine operating between these two limits, is 1 minus T min over T max, or T low over T high, which is 1 minus 310 over 900 degrees Kelvin. And you put that in your calculator. 1 minus 310 divide by 900, and I get 65%. So the Carnot heat engine would convert 2/3 of the energy received in the combustor to work. Our Brayton cycle there, with all of its irreversibilities, only converts 22%. So this guy only has a 22% thermal efficiency, whereas the Carnot, or the maximum efficiency, is 65%. Okay, it's due to the fact that the heat's being received at low temperature for much of the cycle, and we have all these inefficiencies going on in the turbine and compressor. Also has to do with the heat being rejected at temperatures other than the minimum temperature. And so that results in heat transfer across a finite temperature difference outside the device. Okay, we've calculated everything in sight on this problem. I hope you have a good handle on it. Take care, ladies and gentlemen.